Hey everybody, it's been a while since I made a video, and this one's been in the back of my mind for a while, so I'd like to talk about it. I got the notes too, and I finally decided let's just make this video. It might not be perfect, but here we go. I really like elliptic curves, and Diffie-Hellman is also a neat concept about which we're going to get into. And I wanted to show how they work together and how they work independently because I think they're pretty cool. So let's talk about it. So when we communicate online or in other situations, we'll have typically, if we want to encrypt something, we'll have some stuff that we want to encrypt. They usually refer to that as clear text. And then we feed it to a function, an encryption function, in this case AES, it's a popular one, which also will require a secret key of some kind, which it will then use to encrypt the message to make the encrypted message. And then you can take that, and that can be run through the AES decryption function with the same secret key to get the original message back out. So pretty standard stuff. But what's interesting here is that it's the same key used to encrypt and decrypt. So this is called a symmetric cipher. So let's say now that you got your laptop and you want to talk to your bank on your open up a web page and do some banking or something. So it would be nice to use some sort of encryption so people can't see what's going on between you and the bank. So how would this work using the symmetric encryption? You might, for example, say, well, over the communication lines, say to the bank, what secret key should we use? And the bank will say, let's use this random, key I just made up. Problem is, if there's anybody listening on the line between you and your bank, they can hear the same key that you're going to be using, and they'll be able to decrypt and listen in on the traffic going in both directions. Even worse, they could probably reach in and change some of the data and encrypt it using the same key, so it looks like it came from you, which could lead to even further problems. So this is something we obviously want to avoid. Well, the major question then is, how do we establish an encryption key? How do we swap the key even when there's bad guys listening in? And that's where Diffie-Hellman came along. But before we go too far in that, I want to talk about some elliptic curves. So imagine for our example that we have a simple calculator shown up here, and I've crossed out the multiply and the divide. All it can do really is plus and minus, and for what we're talking about, the plus is really all we're going to be doing. So let's see. So we have a dumb calculator, and then over here we are reviewing two basic laws of addition. The order in which you sum things up doesn't really matter. I think we all know that. And it's sort of related, the associative property, where you can change which parts you add together first, and essentially the order again. It's sort of, I always kind of feel they're both sort of related, but anyway. So 2 plus 3, quantity of that added to 4, or 3 plus 4, quantity of that added to 2. So if we use these rules, we can do something interesting. Let's say you do want to do some multiplication, but we can't use that x up there because it's not there. Let's say we want to do 10 times 2. Well, what we could do is write the 2 out 10 times and then add them together. So how many steps does that take? 1, 2, 3, 4, 5, 6, 7, 8, 9 operations, or 9 steps to accomplish that. Well, if we were clever, we could see that there's some redundancy going on here. For example, we could say we can group these in pairs and then solve the first pair using our plus button. 2 plus 2 is 4. And then take that knowledge and replace all these other pairs with that 4, as I've shown here. If you do that ahead of time and then you do all the pluses, the number of plus steps you're actually doing is 1 to make this pair, and then 2, 3, 4, 5 to finish it off, to add the pieces that you've already calculated together, these 4 pieces. That's good, but we could do a little bit more here. We could actually calculate the 2 plus 2 pair, as we did before. And then, seeing as we're going to do 4 plus 4 twice in the previous one, why don't we just do it once and take that result and substitute it in for this pair over here. So what happens then? Well, we have to calculate the 2 plus 2 and the 4 plus 4. That's 2 steps. And then we got to add all these pieces together. 2, 3, 4. So 4 total steps. Okay, so this gets pretty dramatic if you are adding or multiplying by a larger number. So let's take 3 and do 100 times 3. So how are we going to do that? Well, if we're going to do a bunch of threes, let's do this process where we start with the most basic, the first, a pair of what you're starting with, 3 in this case. And let me click again here. So the red numbers are how many threes we're representing above. This red number, of course, is representing this pair. And once we calculate that this pair is 6, we can then substitute for 4 threes by doing 6 plus 6. There's our 4 threes. And then once we know that, 12, we can substitute for 4 plus 4. So a total of 8 threes and so forth. So by doubling, and let's see, this is 1, 2, 3, 4, 5, 6, 7 operations. We've already done 30 threes. And as we know, 33s is 90. So that's what these numbers in blue add up to, is 90. That's the running total so far. All right, but we're not done yet. We're only at 33s and we need to do 100. So let's keep going here. Well, we could take 24 plus 24 and figure out that is 48. We already did that actually. And then as we go 48 plus 48, that gets rid of 16 and another 16 threes for a total of 32 threes right there. So now we've gone from 30 to 62 with 2 more steps. That's pretty good. But we don't actually want to double again, because if we did 48 plus 48 is 96. If we did 96 plus 96, that would actually be adding 64 more threes. So if we're already at 62, so if we do 62 already, and then we had our additional 64 threes, we're going to be way over the 100 that we're looking for. So we don't want to double. But what we can do is we can add another 32 threes, which is 96. We've already found that out, and use a couple of the pieces that we've calculated earlier. So 12, which was this 4 threes, and then 2 threes here. So that gives us, let me bring that down, so another 32, another 4 and 2. If you add all the red numbers up here, that adds up to 100 threes. And that's 12 operations. Let's count them as far as making the component, or doubling the pairs first. So that's one double. That's 1, 2, 3, 4, 5. We did 5 operations to create all the pieces we're going to be adding together in some combination. Now let's figure out how many steps it took to, or add in the steps to add the pieces. So 5, 6, 7, 8, 9, 10, 11, 12. So a total of 12 operations just to do 100 times 3. Not too bad, because the old-fashioned way would have been 99 steps, right? If we just did 3 plus 3 plus 3 forever. So this is pretty helpful to do this. Okay, let's look at this from a visual perspective. So instead of 100, let's do 274 times something, because something doesn't really matter. Let's look at it visually. And this is all to scale. So here's 1, and here's doubling it. Here's doubling it again. And we can finally double it, and the piece is big enough I can stick a number in there, so that's 8. So 1, 2, 4, 8, 16, 32, 64, 128. You can see these steps are getting pretty big. And obviously to get to 274 over here, we do not need to go any further. If we doubled, we'd be way off the page. Even if we added another 128 piece we've already made, that would be too far, of course. I think we can fit a 16 if memory. Yeah, so a 16 fits in, and then it looks like a 2 and a 1. So if we do the math, 1 plus 2 plus 4 plus 8 plus 6, all these pieces, all the way to 128, and then we throw in our 16 piece, the blue, the 2, and the 1, and that gives us our 274 steps. So 7 doublings, 7 different colors, and then all the different additions of those, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so 10 additions of these components. 10 plus 7 operations is 17 operations, or 17 steps, to get 274. So the point here is that the bigger this number gets, we still can get there pretty quick using these doubling, this exponential growth. Excuse me. So there's here's some powers of 2. Since we're doubling, we were talking about powers of 2. We just did 128. That was 7 steps. 32 steps gets you up to a pretty high number. 64 steps gets you up to this high number. And think about it. 64 steps on a computer. Let's say we did this as a program now instead of just a handheld calculator. That would take a blink of an eye. It's just no big deal at all to do 64 operations or fewer. 95, look how big that number is. And 1024 is something with 309. I mean, these are numbers that just, I mean, Avogadro's number, the number of atoms in a mole of material is, I think, something to the 23rd, if memory serves. So, I mean, we're getting past you know, the size of, I think 202 to 256 is something equivalent roughly to the number of atoms in the universe. So you can imagine what 1024 and 4 that's 96. It's big. And sometimes you might hear reference to the second half of the chessboard. That refers to a 64 square board, which is what chess is, 8 by 8. And if you start with 1 and you double and you keep doubling, sorry about that, that keeps keep going and going and doubling, you get pretty high. You're already up to 2 billion in the first half. But where things get really crazy is the second half of the chessboard. You know, 4 billion all the way up to 9, whatever E is. You know, just giant. So exponential growth can really take off very fast, as this just the 2 to the 64 shows. Okay, so I think the next thing, yeah, so the next thing is to talk about elliptic curve math. I have to hit escape here, go to this page and maximize it. All right, so let me introduce elliptic curves, and you'll see why these make sense, or why I talked about the previous math addition problems in a second. Elliptic curves have this form. Let me scroll up here. This very simple form: y squared equals x cubed plus some number a times x plus another number. And by changing the a and the b variables, you can, and which I can do by sliding these back and forth, you can see the curves. The red curve is the elliptic curve itself. Kind of gets different, changes a bit. In fact, a common curve is where x is 0, so like, which is done by, sorry, which is a is 0, so I'll bring that into 0. And I think it is, God, I can't land on that. That's kind of frustrating. There we go. And then b is 7. So this particular curve here is a popular curve. I believe it's used in Bitcoin and others. There's a name for it, like SEPC 7, or I forget. It doesn't really matter. But this is what one curve looks like. The red curve, notice it's symmetric about the x-axis. So every point down below has an equivalent point above, if you will, mirrored over the x-axis. So why does this matter? What's the big deal with elliptic curves? We're almost there. You have to hang in there with me just for a minute longer. Someone figured out that you can come up with a concept called elliptic curve point addition. And this is what's being shown graphically right now. We have 2 points, this blue point, the big blue one here, and the big orange one. And I can drag them around. And you can see what happens is a line is formed between the 2 points. And the way elliptic curves work is this line will only intersect the curve, the red curve, in one location other than the 2 that you've already specified. So in this case, it's this black point right here. So my orange and blue line through it, intersects the curve right here. And that is not the answer, actually. You have to mirror to the other side, to this point here. That is the addition, that is the sum of those 2 points. Now that sounds pretty arbitrary, you know, finding a point, flipping over. Why in the world? Well, you have to do that flip in order to get a property we're going to get to in a second. But just suffice it to say that when you add 2 points in an elliptic curve, you just draw a black line, draw a line between them. Wherever that line intersects the red curve, flip over, and that where you land is the answer. Now, related to point addition is point doubling, where you instead of adding a point to a point, you're adding a point to itself, which kind of doesn't make sense, because if you think about it, there really is no definition for a line that goes through one point on top of each other. I mean, an infinite number of lines can go through that, so that's not good enough to really define it. If you think about it, as I get these 2 points closer and closer together, the black line here is becoming closer and closer to the tangent line. This is a derivative or a limit function in algebra or pre-calculus or whatever. But really, all I'm doing is I'm getting the slope. I'm getting a tangent line. And what's neat is, if I zoom out enough, you'll see that that line, in this case up here, will only intersect the curve again in one location, and in this case it's here, and again you flip down to here to the other side. So adding a point to itself is a little tricky. It's a different set of algebra to get this to work, but to find the equations anyway. But the result's very similar. You just find the line there and mirror down. So both of these situations, either point doubling or adding a point to a point, is very simple algebra. To take this equation up here and solve it for the point and then the mirror of it is just basic algebra. You can do it. You can find proofs of it online. Anyone with an algebra background from high school should be able to solve this. You know, it's calculating the slope of the line and a slope intersect and all that stuff until you find this point. Okay. Now, why does point doubling and point addition mean anything? Let's flip back to my presentation here, and let's see if it allows me to continue. It does. Okay, so I'm just going to restate here. Here's the orange and the blue point, which has some x coordinate and a y coordinate for each. Now it's important, and I just call the resultant point r. But it's kind of just, p plus q, they're both points, gives you an r point, which has also an x and a y coordinate. Now it's not like x1 plus x2 equals x3. It's more complicated than that. Again, we have to do the algebra, find the slope and all that, but it's no big deal. Also, point doubling, a point plus itself, which is kind of referred to as 2p if you think about it, 2 times that point, gives you some resulting number. Excuse me, some resulting point. So those are the two concepts of point math in elliptic curve, and with that we could do some interesting things. For example, if we can do 2p, well, we can do 3p, or that's in my example 11p, 11 times p, or adding p to itself 10 times. So we can use, let's say we wanted to do 11 times p, or p plus itself 10 times for a total of 11 p's. How would we do that? Well, we'd start with we only have one point to start with, so we would double that using the tangent line thing we were talking about, and we'd find the resulting point mirrored over, and that's our answer. And then what we could do is so we find 2p, that's the first step, and then if you wanted to, we could then find 4p by taking that resulting point that we got and adding it to itself using the same point doubling idea, and we find another point that we call 4p. And then we can do this again. So this should look familiar now. We got 8p. Let's see, so point doubling, we get to 8p. And now we have all the ingredients we need. If we take 8p and add it to 2p using the first idea, two separate points on the curve, and finding the intersection, and then take the resulting point of that and add it to 1p itself, I guess, you will then land at 11p. And that is the same thing if you had done p plus p plus p plus p plus p plus p, 11 times. You will land in the same place using the old-fashioned method or the tedious method as you will using this point doubling approach, which gives you exponential growth ability. So again, we find 2p, 4p, 8p, all the doubles. We keep doubling the resulting point, and then we add all the components together as needed. So, and I show you could have done 8p plus 2p and then another p, or 2p. So this is the order of operations. So take this point, which is 2p, take this point, which is 8p, add them together elliptically, and then take that result and adding p to it. Or you can take this, do the 8p plus p first. So this is the associative part of math that also applies somehow. I don't know why. It's just amazing. But this also applies to elliptic curves. So this allows warping, meaning you can do a giant number, like 2 to the 256p can be done roughly in whatever number of steps. We saw that it doesn't take much, probably way less than 256. You just do your warping to get to the vicinity, like we showed visually, and then do smaller steps and smaller still until you finally get to the destination. So let me go back up just to make sure that's understood. So elliptic curves offer you the ability to get to some scalar value, this is a number, times p, very slowly, in the tedious method, or extremely fast using point doubling. So that's a big deal. And that means that you can actually find any number, essentially, of p times p, that point, that you want, even if that number is ridiculously large. So that means you can choose a number way out in the middle of nowhere that no one else will ever guess or ever try to guess because it's so large, and find the point on the curve there, and then use that for some purpose, and we'll talk about that in a second. All right, real quickly, when I learned about elliptic curves, the first thing I thought of was, well, in the examples, we're talking like 1 comma 3 or something in that magnitude. This doesn't seem like that would be very hard to guess points to get to a result point. Um, wouldn't that be the case? Well, it turns out that these points are pretty large. Here's the generator point used in that curve I showed before, the x equals, or b is 7 and a was 0 or something. This is in hex form, base 16, to save space. So in decimal, it would be even longer. That's the red is the x version, or the x coordinate, and the x part of the coordinate, and the green is the y. So you can see that this is the starting point, and so all these points that you're going to move to are going to be very, very, very large as well. So point number one you don't have to worry about. Okay, well the next thing is, if you're dancing around this curve, aren't you going to land on like 1.39272, some long irrational number, and then you'll have to keep track of that, and then you go on to the next number and you have round off error because the computer just can't keep track of an infinite number of resolution. And the answer to that is we reduce the curve to an actual finite set of numbers that are integer values, x and y. That's another neat thing about elliptic curves. If you choose the right starting points and you use the right elliptic curve properties, A and B, you can actually stay on integer solutions, which is amazingly helpful for this. It's critical, actually. And finally, how come we don't spiral out into infinity? Because, if you're way out there anyway and you're point doubling or something, couldn't you just keep going off and have the x coordinate, for example, just go to infinity practically? And the answer is yes. You could go way off into the middle of nowhere. I mean, this point here is already pretty far out there, but you can still go further still, such that you would need all the memory in the world to hold on to the x and the y coordinate. So that's no good. So there is something called modular arithmetic to wrap around. So you actually land back into, if you go too far, it wraps around so that you land back into some number less than your maximum that you've specified. And that's modular arithmetic that's used in other parts of cryptography as well. And it's used here too. It's kind of complicated, so I'm not going to get into it now, but know that there is it is dealt with. And to kind of visualize this, here's another example I found of just an elliptic curve. Looks kind of lame, but there you go. And then here is what it looks like when you only take the integer solutions of this curve and its starting point. And if you go over 97, it wraps over on itself. So that's why you can't really see a curve by itself, because it keeps wrapping over on top over itself over and over and over again, modular 97, so that you never go past 97 with your x coordinate. So you're defining the field that you're staying in. And here's what the animation looks like for adding points in this situation. There's the line, and you can see it modular wraps around and will hit that other point that it would have anyway, except it's wrapped inside, and then you flip it around down to there. So we're getting a little off the deep end here, but you can maybe visualize a little bit of what I'm talking about here. This is how it works. So just imagine that just zillions and zillions and zillions of these points, just so many that you just can't map them all and have a table or anything of them. It's impossible. So, okay. Getting back to the man in the middle. I just kind of put everything here. Here's what you do. And the Diffie-Hellman solution using elliptic curves is for you to pick a large random number. It's just a number. And in cryptography, sometimes we call that scalar to differentiate it from a point or something. It's just a number. A very large one. And then you use an elliptic math, you use the point doubling and whatever in elliptic curves to take your first point, called the generator point. Instead of P, we actually use a number called G. You saw that green and red and green point was a G value for one particular curve. Anyway, you take the G for this curve you're working with. I guess this is, by the way, some of these parameters are known between all three parties. We're going to be using this curve, this starting point, the generator point, and all that doesn't need to be kept secret. But what you do is you take your secret letter or number A and you use point doubling, and it's so absolutely huge that it would take you a zillion years to do it manually. But because you know where you're going, you know how big A is, you can use point doubling to get there quickly and solve for this point. All right, so we get a point. And now this bank is doing the same thing. They've picked a large number and they've called it B, and they've done the same thing. They've used point doubling shortcuts to get this done quickly, and they come up with a point BG. All right, and so they send it to you, so you get their point BG. And then what you can do is you can take their point BG and continue multiplying it by your A. So you're essentially just taking their point and you're moving forward. You're continuing to multiply it by your value. So you keep moving point to point to point to point, and you can use the exponential, point doubling and all that to help you. So you get to the answer ABG. So you've basically taken this point G and you've done point doubling and elliptic math to get to the A times B point. So this is a giant number, A times B. If A is huge and B is huge, then A times B is even ridiculous. So trying to find that point, that number point of the generator would just take ages. I mean, impossible unless you knew where you were going ahead of time. Anyway, so you find ABG, and what happens is the bank kind of does the same thing. They received AG from you. They don't know what A is, but they do know what their B is. So they can take your point, AG, and continue multiplying it by B using elliptic math, and they will come to a point, and that point, they'll call it BAG. You have your point, ABG, and they are the same because A times B is the same as B times A. So you've both arrived at this crazy point way off in the distance that this guy, the thief, the man in the middle, cannot get to, because he doesn't know A, nor does he know B, and he doesn't know how to. The only way he could do this, the way he could find this point, would be to somehow know which, well, both of them really. If even though he learns point AG and point BG because they're sending across the wire, he can't figure out A or B, which means he cannot figure out ABG with the shortcuts. So now once you have that, you can take, for example, let's go back to our AES example. You can take your message. Maybe you take the x coordinate of ABG to encrypt, and then the bank takes the x coordinate of BAG, which is the same point, so it's the same information, and uses it to decrypt. And that's how you share a secret key using elliptic curves to get to a symmetric key cipher and not have anyone be able to intercept it en route. So there's the explanation. I don't think I have anything else. That's it. Hope that was interesting and clear. Ask any questions down below and I'll do my best to answer them. Take care.